Let us consider multitone AM now. In singletone AM, we have seen that message signal having the single frequency component. Now in the multitone AM, we should have more than one frequency component in the message signal. I am taking the multitone signal here with respect to 3 frequency components so that we can apply for 2 frequency components or 3 frequency components as per the required question. Now let us consider the multitone AM with respect to 3 frequency components in the message signal M of t. So this I am considering that A1 cos 2 pi f1t plus A2 cos 2 pi f2t plus A3 cos 2 pi f3t. Observe that I have taken 3 frequency components within this message signal M of t, where f1, f2, f3 are the frequency components in this message signal. I am taking the order that f1 value greater than f2 greater than f3, and then I am considering that the amplitudes of these 3 message signals A1 greater than A2 greater than A3. Let us consider this scale because of plotting the spectrum of this multitone AM signal. This scaling is helpful for us. Which one parameter is more, which one parameter is less. To plot that spectrum AM graph, we need these relations. Fine. Anyhow, let us consider that the carrier signal here C of t first, that is AC cos 2 pi fct, high frequency carrier signal I am considered, and then the general form of AM if I consider. In that AM signal, let us take this message signal. First I will write the general form of AM signal, that is AC into 1 plus Ka M of t cos 2 pi fct. In this general form of AM signal, let us consider this message signal as this multitone message signal. Let us substitute this M of t here in this equation, that is 1 plus Ka. This M of t is A1 cos 2 pi f1t, and then Ka A2 cos 2 pi f2t, and then Ka A3 cos 2 pi f3t. This is all multiplied with cos 2 pi fct. Now let us multiply this cos 2 pi fct inside of this expression, and then I am taking this Ka A1 as mu1 modulation index, and Ka A2 as mu2, and Ka A3 as mu3. Let us consider now this expression simplified as AC cos 2 pi fct first term, and then AC mu1 cos 2 pi fct multiplied by this term cos 2 pi f1t, and then this cos signal multiplied with cos 2 pi f2t term. We are taking that AC mu2 cos 2 pi fct multiplied by cos 2 pi f2t, and then the third term it is mu3 cos 2 pi f3t. It is multiplied here AC mu3 cos 2 pi fct multiplied by cos 2 pi f3t. If we observe in this expression, we have cos C cos D expansions 3 times. Let us take the trigonometric approximation to divide this cos C cos D term in terms of cos C plus D and cos C minus D terms. I am dividing these products in individual cos terms like this. First term it is as usual AC cos 2 pi fct, and then this is AC mu1 by 2 cos C plus D term, that is cos 2 pi fc plus f1t, and then cos C minus D term AC mu1 by 2 cos 2 pi fc minus f1t. Observe I have divided cos C cos D into cos C plus D cos C minus D terms. Similarly, we have to apply the same approximation for these 2 terms. I will write these 2 expansions here. Next we will get AC mu2 by 2 cos 2 pi fc plus f2t I will get, and similarly here AC mu2 by 2 cos 2 pi fc minus f2t. For this second cos C cos D product, similarly we can apply for this f3 term. So in the similar way we will get AC mu3 by 2 cos 2 pi multiplied by fc plus f3t, and then the last term it is AC mu3 divided by 2 cos 2 pi fc minus f3t. Observe that we have taken that carrier frequency here greater than f1, f2 and f3. So that we are getting that totally here 1, 2, 3, 4, 5, 6, 7 cos individual terms. So for each cos term we will get 2 impulse functions in the spectral diagram. So let us consider the Fourier transform of this multitone AM signal. This is what the multitone AM signal, the time domain expression, final expression. For this final time domain expression, if we take the Fourier transform both sides, we will get the frequency domain representation of this multitone AM first. After that we can plot the diagram and then we can calculate the bandwidth as per the requirement. So first let us write the frequency domain representation for this time domain expression. So this Fourier transform of first term, it is AC by 2 del of f minus fc plus del of f plus fc. This is what 2 delta functions associated with this carrier cos term. Next, these 3 terms are upper sideband terms, these 3 terms are lower sideband terms. So let us consider these 3 terms and these 3 terms as per their corresponding Fourier transforms. I will write the expression here. AC mu 1, this term divided by 4 will get, and delta functions at this frequency will get that del of f minus fc plus f1 and then del of f plus fc plus f1. So observe these 2 delta functions we are getting for this first upper sideband term. Similarly, we will get one more term, one more 2 delta functions for this lower sideband term. Let us write these terms here. I will get this lower sideband term Fourier transform. This is AC mu 1 by 4 and del of f minus lower sideband frequency fc minus f1 here, and second delta function f plus fc minus f1. Observe these 2 delta functions related to the first LSB term here, fc minus f1. Similarly, we have to write for these 4 terms. I will write just below this so that we can compare easily and we can write it easily. So AC mu 2 by 4 and simply f1 we can replace with f2 here. That means del of f minus fc plus f2 plus del of f plus fc plus f2. This is related to the second upper sideband term we have. Similarly, for second lower sideband term, f1 we can replace with f2 now. Same expression we will get, and f1 replacing with f2, we will get the second LSB Fourier transform. So that we can get here AC mu 2 by 4 and then del of f minus fc minus f2 plus del of f plus fc minus f2. This is what second LSB related Fourier transform expression. Similarly, we can write upper sideband, the third one we can write here AC mu 3 by 4 this time, and then f2 we can replace with f3. So we will get fc plus f3 here, and this term del of f plus fc plus f3, and the last term third lower sideband term cos term, this Fourier transform. In this expression we can replace f2 with f3, so that AC mu 3 by 4 del of f minus fc minus f3 and then del of f plus fc minus f3. Like that we are getting the delta functions for each cos term. We are having the 2 delta functions at their respective frequency components and the amplitude divided by 2. We got that frequency domain representation of multitone AM here. If we take the graphical representation for this multitone AM, we can find the bandwidth for that multitone AM. So let us plot the spectrum for this multitone AM. Let me erase this content. let us plot the spectrum for this multitone AM and then let us calculate the bandwidth for this. So I am plotting this spectrum in the frequency domain. Let us take frequency here and the multitone AM. The first delta functions we are having at plus or minus Fc with the corresponding amplitude AC by 2. I will take Fc here with AC by 2 amplitude, the carrier frequency components, both left side and right side. Next, we are getting that upper side band, first upper side band frequency components, both right side and left side. So at Fc plus F1, this is the right side delta function, this is the left side delta function we have. At Fc plus F1, I am taking this Fc plus F1 here. This is having amplitude AC mu1 by 4. Observe that the amplitude of this upper side band term, we are having that AC mu1 by 4. So similarly, left hand side we are getting that. Let us take some graph here. This is AC mu1 by 4 at minus Fc minus F1. Let us consider that the first LSB term here at the frequency component Fc minus F1, this is the right side delta function, this is the left side delta function for Fc minus F1. So that the right side function we are getting somewhere here. This is Fc minus F1 frequency component. Similarly, left hand side we will get at minus Fc plus F1 frequency component. Observe that these components should have the same height and these two components should have the same height. And then the second upper side band component, if you take Fc plus F2 frequency component, we have already assumed that F2 is less than F1. I have taken that assumption that F1 greater than F2, F2 greater than F3. That means F2 value we have to take lesser than F1. So let us plot this component Fc plus F2 somewhat lesser here. And this frequency component, it is having the magnitude AC mu2 by 4. Let us plot there. That is Fc plus F1. And then same component here minus Fc minus F2. Observe that this component Fc plus F2 and the reflection we will get here minus Fc minus F2. So somewhere here we will get this plot minus Fc minus F2. This should have the same amplitude with that. Let us take this amplitude same as this amplitude. This is for upper side band second term. Similarly, lower side band second term, if you see, this is the right side function, this is the left side function. We will have AC mu2 by 4 same amplitude. For this LSB, Fc minus F2. So with respect to Fc, F2, I can take minus Fc minus F2 here, same amplitude. That means Fc minus F2 component. And the reflection of that one. So that is between, observe that Fc to Fc minus F1, between the carrier component and this LSB component, we are getting this component. This reflection we will get that this side Fc to this one, this LSB, this carrier component, in the middle of this one only we should get that. So that I can take this component somewhere here, that is reflection of this component minus Fc minus F2 plus F2 we will get, right. This is the second LSB component with respect to this one, fine. And if you observe, we will take LSB component, the third upper side band component if we take, this is the third upper side band component, it is having the amplitude AC mu3 by 4, the location Fc plus F3, and we know that F3 is less than F2. So let us plot first upper side band terms here. So upper side band term should have frequency component Fc to Fc plus F2, I am writing here, that is Fc plus F3. This is upper side band component for F3, and lower side band component or the right hand side component for this is Fc plus F3 with respect to this left hand side component we have to plot first. That is from the reflection you will get somewhere here. This is Fc plus F3, the reflection minus Fc minus F3 you will get, and this amplitude will be a little bit lesser than that one. So this component should have amplitude lesser than that. You will get the upper side band component for the third one. These two terms I have plotted here and here. And then let us consider the LSB component for the third frequency Fc here. This is right side component, that is left side component. Observe that AC mu 3 by 4 amplitude here for both LSB and USB. Let us take that last term delta functions, that is Fc minus F3 right side component. Similarly left side component somewhere here. This is component Fc minus F3, this component reflection, that means minus Fc plus F3 you will get. These are the 6 components delta functions right side and 6 delta functions on left side, and along with that one carrier component delta function extra. Totally 7 left side, 7 right side, 14 delta functions we are having for this 7 cos functions. This is what the plot of multitone AM. Now we can calculate the bandwidth of any signal by taking the range of positive frequency components of that signal. Here if you observe, the positive frequency components you have to consider. The range of positive frequency components is nothing but the bandwidth of that signal. The highest frequency component we are having that Fc plus F1 minus the lowest frequency component in this positive spectrum we are having that Fc minus F1. So that this is equal to Fc gets cancelled, we will get the 2F1. If you observe the message signal, we have the 3 components in the message signal F1, F2, F3, and I have assumed that F1 is the highest frequency component in the message signal, and the bandwidth of a baseband message signal is nothing but the highest frequency component of that signal, that is F1 here. So F1 is nothing but the bandwidth of the message signal. So finally what we can conclude here means bandwidth of this AM signal is nothing but 2 times the bandwidth of this message signal. As per the general conclusion, for any kind of amplitude modulated signal, the bandwidth requirement for the AM signal should be equal to twice that of the bandwidth of the message signal. That we can verify with this conclusion. Now let us calculate the power components of this multitone AM signal. We have calculated the bandwidth of this multitone AM signal. Now to calculate the transmission power of this multitone AM, I have kept this equation as it is without erasing. So by using this equation, the time domain multitone AM signal, let us calculate the total transmission power requirement for this multitone AM. Each cos signal having some amplitude here. Amplitude square divided by 2 gives the transmission power of that particular cosinusoidal signal here. So here amplitude AC is there, so that the transmission power for this it is AC square by 2, and then the amplitude here it is AC mu 1 by 2, so that we will get AC square mu 1 square by 8, and the next term we are having that AC mu 1 by 2, so that we will get AC square mu 1 square by 8, and then similarly we will get that for this term AC mu 2 by 2 we will get the power AC square mu 2 square divided by 8, and this also same amplitude component, that is having power AC square mu 2 square by 8, and this term having AC mu 3 by 2, that is having the power amplitude square divided by 2, that is AC square mu 3 square divided by 8. Same power for this component, the last component, that is AC square mu 3 square divided by 8. Let us simplify this expression by taking AC square by 2 common. I am taking AC square by 2 common here, so that from this it is 1, and these two if you observe, after taking AC square divided by 2 common, we will get that mu 1 square by 4 here and mu 1 square by 4 here. Combinedly mu 1 square by 2 I will write here. These two getting mu 1 square by 2 means these two should get mu 2 square by 2, and similarly the last 2 terms should give mu3 square divided by 2. Let us further write this expression as AC square by 2 is nothing but the carrier signal power, that is I am writing as PC here. So that this expression I am writing as PC multiplied by 1 plus mu1 square plus mu2 square plus mu3 square divided by 2. Observe that the transmission power, it is for multitone similar to the single tone AM transmission power. The single tone AM transmission power, we got the expression PT is equal to PC multiplied by 1 plus mu square by 2. Similar to that, we can write this expression as for multitone AM PT is equal to PC into 1 plus mu suffix T square divided by 2, where mu T is the overall modulation index of AM. We are writing this one as overall modulation index of AM, which gives that mu T square is equal to mu1 square plus mu2 square plus mu3 square. Observe that the message signal having 3 frequency components in this AM, that is why we are getting that mu1 square, mu2 square, mu3 square. If we get more frequency components, this corresponding modulation indexes will be added here for this overall modulation index. So let us write this multitone AM power component relation in comparison with single tone AM power component relation. From that we can write the expressions for currents relation and voltages relation in this AM. I am writing here as a comparison table for this single tone AM and multitone AM, the 3 relations. First, I will write the power relations for these two. Here transmission power requirement, that is equal to carrier power multiplied by 1 plus square of the modulation index divided by 2. This is what the power relation we got. Similarly for multitone we got this much, that is PT is equal to PC into 1 plus overall modulation index square divided by 2. Now we know that power is directly proportional to the square of the voltage and power is directly proportional to the square of the current. So from that we can write that voltages relation from the power relation as total transmission voltage square is equal to carrier signal voltage square into 1 plus square of the modulation index divided by 2. For the single tone AM, this is the relation for voltages of total modulated signal voltage and carrier signal voltage. Similarly, here for multitone, we can write similar expression VT square is equal to VC square into 1 plus overall modulation index square divided by 2 here. Similarly, we can write the currents relation here. This is total signal, modulated signal current square is equal to carrier signal current square into 1 plus mu square by 2 here. And multitone AM we are having that IT square is equal to IC square into 1 plus overall modulation index square divided by 2. These are different relationships between currents relation and voltages relation and power components relation in comparison with a single tone, the multitone AM we have.